This conference will now be recorded.
Hello everyone. Last day we have started just at the end chemical properties of haloalkanes, and under that we have seen there are total 4 types of reaction. And among these 4 types of reaction, 2 types of reactions are mostly important. The first one is nucleophilic substitution reaction and the second one is elimination reaction. So today we are starting with nucleophilic substitution reaction, though we already have some idea because this slide I have already started, but it is not finished yet. There are so many other things that we have to know. Here in other slides in today's class that we are going to discuss after seeing this primary idea about nucleophilic substitution reaction, then we will see what is its mechanism that are involved in stereochemical aspect and some related problems. So here the RBR, that is alkyl halide, is C2H5 then Br. So you can also write it as Rx. And different types of nucleophiles we are using, but the reagent that we are using, they are not directly the nucleophile. So in this case, the nucleophile is HO. Here the nucleophile is directly the ammonia, then KCN, AgCN. Now both are source of CN, but remember, depending on what kind of cyano ion containing compounds you are using, depending on that, product will be different. So in case of KCN, you are getting RCN, and here you are getting RNC. Similarly, when it is KNO2 and AgNO2, same thing as you are observing in case of KCN and AgCN. Here also KNO2 and AgNO2. See, depending on what is the source of NO2, depending on that, 2 different types of products we are getting. This is RONO. That means carbon oxygen bond is formed. It is not called ethyl nitrite. ONO is nitrite. But when carbon nitrogen bond is formed, now the name is different, it is nitroethane. Okay, in both cases these are the byproducts. Then if your attacking reagent is that is reagent is R prime ONA, but actual nucleophile is R prime O minus. Na plus is the counter. So see, the nucleophile is joined to the R group, which is C2H5, and you are getting C2H5 OR prime. Then the next reagent we are using, it is actually sodium salt of acetylene. Acetylene is H3 triple bond, then CH. Now this H is acidic in nature because this carbon is sp hybridized, so it can stabilize the negative charge after removal of this hydrogen. So if this hydrogen is replaced by some metal ion, for example here we have Na plus, then it is sodium salt of acetylene. So this reagent that you are using here, the actual nucleophile is basically HC triple bond C minus. So this is a nucleophile. So see, this nucleophilic part, it is attached to the R group. Then the next reagent, R prime CO2 Ag. Here R prime CO2, that is actually the nucleophile. So carbon oxygen bond is formed. R prime COO, that is attached. So this part is the nucleophile. Okay, Ag and Br together, it is making the byproduct AgBr. So here we will see, if we elaborate this part, that when it is RCN and when it is RNC, that is 2 different types of products. This is actually RCN, right? And C2H5NC, it is RNC. Try to understand the difference. When it is RCN, then you have carbon-carbon bond. So here you have carbon-carbon bond, and this is known as cyanide, alkyl cyanide. So suppose if the R group is ethyl, it is ethyl cyanide. If it is methyl, methyl cyanide. Fine. Bonding of alkyl through carbon. So carbon-carbon bond is present. But in RNC, now nitrogen is attached to R, and this is known as isocyanide. So if R group is methyl, suppose, then it will be called methyl isocyanide. And here bonding of alkyl group through nitrogen. So here you have carbon nitrogen bond, not carbon carbon bond. Okay, so this is the difference. And here we have 2 bonds between nitrogen and carbon, and the third bond, as you can see, it is denoted by arrow sign. This is actually coordinate bond. Now some features about these reactions. There are certain groups that consist of 2 nucleophilic center. For example, KCN and AgCN, if you consider this, that is cyano, this particular ion, if you consider, here you have 2 nucleophilic center. So they are actually known as ambidentate nucleophile. Now when it is KCN, that is CN, when for CN, when the source is KCN, potassium cyanide, it is basically ionic molecule and it provides cyanide ion in solution, which is ambidentate nucleophile, and it binds with the carbon site to form the major product. But if the CN source is silver CN, then it is covalent in nature and it forms isocyanide as the major product. We are not going into the details, just remember, because of the difference in their nature, KCN is ionic, AgCN is covalent, so different types of compounds you are getting. Fine. Now just like KCN and AgCN, if you are using KNO2, which is analog of KCN, or you are using AgNO2, which is analog of AgCN, fine, then also you are getting different types of product. So here you have carbon oxygen bond, here we have carbon nitrogen bond. So this is the difference. Fine. So some more light if we give on it, you can see NO2, KNO2, this is when bonding with through nitrogen, that is when you have carbon nitrogen bond, it is called nitro. So here nitro, you will call it in this way when it is attached through nitrogen. Fine. As you can see here, nitro. So here you have carbon nitrogen bond. But if it is attached to the alkyl group through oxygen atom, the name is now different. It is now nitrito. So it will be like this: R O N O. So suppose R group is methyl, it will be like this: methyl group, then O N double bond O. So here you have carbon oxygen bond. Okay. And if it is NO2 group, then it is like this: H3C N double bond O plus minus. Fine. So depending on what kind of compounds you are getting, the name is different. When you are using KNO2, you are getting ethyl nitrate because carbon oxygen bond is formed. But when you are using AgNO2, then carbon nitrogen bond is formed and the name is different. Now it is called nitroethane because your alkyl group is ethane, and if it is methyl, it is nitromethane. Fine. So this is all about that is different types of nucleophilic substitution reactions. Examples. Now we will go into the details. But please tell me if there is any doubt in this primary idea that we are having in this particular slide, because after that we will go into the details. That is the mechanism of nucleophilic substitution reaction, because there are two main types of mechanism which are very important from exam point of view, and also the stereochemical aspects of this nucleophilic substitution reaction. So in this slide, if there is no problem, may I proceed to the next slide? Is it fine? Here one more point also we have. Suppose if the R group that we have considered for Rx, suppose if it is vinyl, vinyl group is C2, that is CH2 double bond CH, that is CC double bond, and then X, and X is suppose Cl. So this is vinyl chloride. Now this is not very reactive towards nucleophilic substitution reaction. Why? Because in this case this carbon is sp2 hybridized. Okay, and removal of chlorine, that is the leaving group, is difficult here. Now the one reason is this is sp2 hybridized, so the bond strength of carbon chlorine it is high, and also because of this type of resonance here double bond character is generated between carbon and chlorine. So after resonance, the structure that you are getting now negative charge on this carbon, then CH, then double bond chlorine. Chlorine is now positive. So because of this type of double bond nature between carbon and chlorine, now breaking of this CX bond, that is carbon, chlorine or bromine, whatever it is really difficult. So that is why nucleophilic substitution is not possible. So see all these examples that we have, we are seeing here, it is based on this structure, which is sp3 carbon, not sp2. Fine. Now we are going to mechanism. So when it is mechanism of nucleophilic substitution reaction, remember there are two important types. Fine. The first type is a bimolecular nucleophilic substitution reaction, which is denoted by this term, and the second one is unimolecular nucleophilic substitution reaction. Now both these terms that you are seeing, it is absolutely same, only difference in the first case it is 2, second case it is 1. Now S we are using because it is substitution reaction, S for substitution. Then what is the meaning of N? N means nucleophilic, so that is why it is SN. And 2, what is the significance? It is bimolecular. When you will go into the details, you'll be easily getting the idea why it is bimolecular. And unimolecular, that is only one molecule, that is why it is 1. So that is the difference. So in the right hand side in this box, you can see all these terms, 3 terms that are mentioned here, S, N, and then 2 or 1. So it has different meaning. It is substitution, N means nucleophilic, and 2 means bimolecular. If it is 1, it is unimolecular. Okay. So first we will be focusing on SN1, which is type B, because it is easy to understand. So that is why we are starting with B. So here the starting material that we have taken, that is alkyl halide, it is tertiary butyl halide, because we have CHC, this carbon with which halogen, that is the leaving group, is attached. That carbon is attached to 3 more carbon. So here this carbon is basically 3° carbon, and this group is tertiary butyl group because total 4 carbons are there, so it is butyl. And when in butyl group there is a carbon which is attached to 3 more carbon, then it is called tertiary butyl, because this carbon is 3°. Now when it is substitution nucleophilic unimolecular, that is SN1, remember there are total 2 steps. It is not single step, it is 2 steps. Now whenever there are 2 steps, obviously one of the step will be slow, another step will be fast. Now the slow step is the first step. As you can see, it is written here, and that is why slow steps are always rate determining step. So when I am saying rate determining step, that means what? This step, that is step 1, that will decide the overall speed of the reaction. So that is, it is called rate determining step, because in this case there are total 2 steps. And when we are saying that what is the rate of the reaction, obviously individual rate of these 2 steps you have to consider. But among these 2, as the first one is slow, so if somehow you can make this slow step, somehow you can make it very fast, obviously it will make the overall rate of the reaction, that is the combined rate overall, also fast. So that is why our aim, our purpose will always be to make this slow step fast. And how you can do so? You can do it by making the intermediate that is formed here, by making the intermediate very stable. So that is why here we have taken 3° alkyl halide, because here the first step is removal of this carbon halogen. So X is removed and you are getting a positive charge over this carbon. Now this carbon is 3°. So this is 3° carbocation. 3° carbocation is very, very stable because of the 3 plus I effect coming from 3-methyl. Okay, so that is why in SN1 reaction 3° alkyl halide mostly taken, because it will give you good result. Because here our purpose is to make the intermediate. This is intermediate. I am writing I in short. This is the intermediate. Intermediate means which is not the final product, but it is formed in the reaction medium. It is not very stable, but it is compared to transition state, it is more stable. Fine. Now come to the second step. In the second step, what is happening now? Nucleophile is coming into the picture, and this nucleophile, which is carrying some negative charge, or it may be some neutral molecule having lone pair. So this will attack this positively charged carbon. As a result, now you are getting carbon nucleophile bond. Okay, fine. Now why it is called unimolecular? Because for this reaction, when you will consider the rate of the reaction, basically the slow step is important. Among these two steps, the second step is fast. It is not very important because it will always occur at a very high speed. But that step which is basically slow, if somehow you can make it fast, basically now you can get overall high speed of the reaction. So that is why in the slow step, here only one molecule is involved. Which molecule? It is alkyl halide. Nothing else is mentioned in step 1. So as only one molecule is involved in the rate determining step or slow step, that is the first step. Fast means FIRST, not FAST. So that is why it is called unimolecular. So rate expression will be rate is equal to rate constant K, then concentration of alkyl halide, which is Rx. See, only one species is involved. Only the concentration of one species is involved. That is why it is unimolecular. Okay. So reaction will follow first order kinetics, or we can say that the rate determining step in this reaction is unimolecular. Fine. Not the second step is unimolecular. We are talking about the first step only. FIRST, first step. Step 1. Here what happens? The carbon bromine, better I write X because that is more general. Carbon halogen bond breaks and it forms a carbocation and halide, that is X minus. So this step is slow and hence it is the rate determining step, that is RDS, rate determining step. And in the second step, now the nucleophile immediately reacts with the carbocation immediately, that is why it is fast. It takes place very fast, right? And it doesn't affect the rate of the reaction. So whenever there is any fast step, suppose this is very simple example, here you have only 2 steps, but suppose in any reaction you have total 4 steps, 1, 2, 3, 4, multi-step reaction. So it may be there are total 4 steps. Now among these 4 steps, suppose second step is rate determining step. So though there are 4 steps, but as the second step is rate determining step, so if somehow you can increase the speed of this slow step, basically it will increase the overall step. So here significant step is second step because it is controlling the overall rate. It is a slow. Other steps are not slow, they are fast. So you don't have to focus on them much. They do not affect the rate of the reaction. Only that step which is slow, that affect the overall rate of the reaction. Okay. Any doubt in this slide? Some more aspects related to SN1 reaction we will see. SN1 reactions are generally carried out in polar protic solvent. Next question is, what is polar protic solvent? Now, when we are saying polar protic solvent, obviously it is polar. Polar nature is there. And the second term is protic. Now, protic means it is related to the term proton. That means active hydrogen must be present. So in this solvent, if you remove H plus, that is proton, then negative charge will be generated on some electronegative atom. And it may be nitrogen, it may be, mostly it is oxygen, but it may be nitrogen also. That means in this solvent, there must be presence of OH bond or NH bond like this, because these hydrogens are active. Why I am calling it active? Because after removal of H, as H plus, that is electron deficient, there will be negative charge over oxygen or over nitrogen. So if you have this type of OH or NH group, then only you can say that these solvents are polar protic solvent. So very good examples are water, because you have OH group, alcohol, you have OH, acetic acid, you have OH. Now it involves the CX, that is, now come to the actual alkyl halide, which is containing carbon halogen bond. So carbon halogen bond breaking, for which energy is obtained through solvation of halide ion with the proton of protic solvent. Now remember, what is the first step of SN1? It is removal of carbon halogen, that is breaking of carbon halogen. So I am writing it here again. The first step is formation of R plus. and here X minus is removed as leaving group. That means if X minus, which is the anion, and R plus, which is basically the positive charge, you can call it cation. So if the solvent molecules, they can stabilize this cation and anion, then what will happen? This step will be fast because this is slow, and our aim is to make it fast. So if you are using polar protic solvent, they will stabilize R plus as well as X minus. So this slow step, now it will be fast. Now how it is doing so? See here, suppose the starting material is R3CX. That means the cation will be R3C plus. So this is R3C plus, the cation. Now as it is cation, here we have some water molecules, but see the orientation of water molecules, it is important to notice. How the water molecules are drawn here? See, in all cases oxygen is facing towards positive charge, right? Not hydrogen. But when it is the anion, that is, suppose it is Br minus, now hydrogens are facing towards Br because hydrogens are the positive side, right? That means water simultaneously can stabilize this positively charged R3C plus as well as the leaving group Br minus or Cl minus. Okay, so this is the reason polar protic solvents are used. Now polar solvents, low concentration of nucleophiles and weak nucleophiles, all these factors can favor SN1 mechanism. So polar solvent you have to take, then concentration of nucleophile, which is basically in the second step, that should be low. Now if question is arising in your mind why it is so, that we will discuss later when there will be separate slide which is based on factors on which this mechanism is dependent. That in that portion we will discuss it in detail. Right now just remember, polar solvent, low concentration of the nucleophile in the second step, and also weak nucleophile. If this type of conditions are present, it will favor SN1. Remember, there is another mechanism also that we not yet discussed, which is SN2. So in that case you will see these factors will be now reverse. That is high concentration of nucleophile, strong nucleophile, that will actually favor SN2 but not SN1. So when it is SN1, you have to take polar protic solvent, low concentration of nucleophile, weak nucleophile. So these are the features that will be better for SN1 mechanism. Next is reactivity order of alkyl halide. So what type of alkyl halide you have taken, that is also important. Depending on that, it may be SN1 or SN2. So if it is 3 degree alkyl halide, for example, if it is R3CX, obviously it will generate R3C plus carbocation, which is very stable. So that is why 3 degree will give you best result. After that, it is 2 degree. That is, if the nature of the starting material is like this, R2CH, then X. And if it is 1 degree, it will not give you a better result. It is very poor substrate for SN1. So this is basically the order: 3 degree, 2 degree, 1 degree. Now in SN1 reaction, partial racemization occurs because of the possibility of frontal attack as well as backside attack. Now what is meaning of racemization? We will just discuss it after 1 or 2 slides. After this, right now just focus that it is racemization mostly that will take place in SN1. Now here the carbocation that is formed, we know that carbocation, this carbon is sp2 hybridized, which is planar in nature. Now if it is planar, see here box is drawn because it will help you to understand its planar nature. Now suppose this plane is perpendicular to the screen of the laptop, the nucleophile, it can attack from back side or from front side. So both side attack is possible. So here this carbon is containing all 4 different groups. So this carbon is chiral, this is also chiral, and here nucleophile as it is, it can attack from both sides. Possibilities there 50%, 50%. So that is why we can get two different enantiomer, and racemization is possible. Now details, that is stereochemical aspects of this mechanism, we will discuss it separately. Fine, but except this last point, if there is any other in the other points, if you have any doubt, you can mention please. If there is no doubt, we can proceed to the next slide. So after having this substitution nucleophilic bimolecular, after that we will start stereochemical aspects. SN2, after finishing SN1, now we will see what is SN2. Here the substrate that we have taken, R1, R2, R1, CH, there is R2, and then X. So see, this is 2-degree alkyl halide, right? Because this carbon with which X is attached, that is attached to 2 more carbon. So it is 2 degree. This reaction involves formation of a transition state. In short, we also call it TS. And transition state, that is mostly written within third bracket, because it is very, very unstable. That if you compare stability of intermediate and transition state, this is even more unstable compared to intermediate. And there is a sign like this, equal sign, then there is a slash. So this sign, it may, if it is present over the molecule in the right hand side, it means it is denoting transition state, and this is very, very unstable. It involves and remember, it is a single step reaction. In SN1, what you have seen, it is 2-step reaction, but now it is single step. Okay, this reaction involves formation of transition state in which both the reactant molecules are partially bonded to each other. What is the meaning of this line? Here, the attack of nucleophile and the breaking of this carbon halogen bond, both are taking place simultaneously. That means in the transition state, actually these lines, it should be in dotted nature. Dotted line means what? That the bond between carbon and halogen, it is just starting to cleave, and the bond between nucleophile and carbon, it is just starting to be formed. So that is why there is a dotted nature. So the bond between nucleophile and carbon is gradually formed, and the bond between carbon and halogen is gradually broken. Okay, so this is the transition state. Here there is a first arrow, then there is a second arrow, but don't think it is a 2-step reaction. Yes, it is true, we have used 2 arrows, but it is not 2-step reaction, it is single-step reaction. But why we are having 2 arrows here? Just to understand this transition state, because this transition state, how it is actually, we should understand that properly, because based on that other factors are also dependent. And finally X is removed and you are getting carbon nucleophile bond, and this is inverted product. We'll come to that point later. Now why it is bimolecular, which is the main difference with SN1? Because in SN1 that is also substitution, that is also nucleophile, but that is unimolecular. But now we are using the term bimolecular. The reason is it is single step reaction, so you don't have any rate determining step, no question of that. Now in this single step reaction, both nucleophile as well as the alkyl halide, both are mentioned, 2 molecules are mentioned, so that is why it is bimolecular. And it follows second order kinetics, obviously. Single step, that is 1 step. The attack of nucleophile always occurs from the opposite side. In SN1, what you have seen, remember, it can attack from back side, it can attack from front side, because the structure of this carbocation is planar. But now the case is different. Nucleophile can only attack from the back side, because the other side, there is already the presence of leaving group. So there is no space, nucleophile can go there. So it has to be in the back side, that is where X is present, nucleophile is just on the opposite side. So attack of the nucleophile occurs from the opposite side, in which halogen is attached, thereby inverting the conversion of the configuration of the product. So when you will see the stereochemical aspects in other slide, you will be getting this idea of that why it is inversion. Right now I'm not going into the details. Right? So this is a rate expression. In the previous case, we have seen it is rate equal to K, rate constant, and only the concentration of Rx, that is alkyl halide. But now you also have the concentration turn of nucleophile. So as two species are involved, that is why it is second order, that is why it is bimolecular. So it depends, rate of the SN2 reaction depends upon the concentration of both alkyl halide as well as the nucleophile. Okay. Now the reactivity order of halides, that is alkyl halides, in case of SN2, it is completely reversed. Now 1 degree first, 2 degree first, and 3 degree. In the previous case, we have seen it is 3 degree, 2 degree, 1 degree, but now it is reversed, and that has to be. Why? Because here we do not have any carbocation intermediate. But if you take 3 degree, there will be so much steric hindrance for the nucleophile. Because 3 degree means what? Carbon will be attached to 3 more groups, right? But suppose if it is 1 degree, carbon is attached to only 1 carbon. So it will be comparatively less sterically hindered for the nucleophile. So nucleophile will prefer 1 degree alkyl halide, where this carbon, a 1 degree alkyl halide, very good example is CH3, CH2X. So this carbon is 1 degree because it is attached to only 1 carbon. The attack of the nucleophile for this type of substrate, it is very facile process, right? But suppose if it is CH3 whole 3 then CX, that means tertiary butyl. So it is really difficult for the nucleophile because of the steric hindrance. Okay. Now steric hindrance we have not discussed in SN1, because in SN1 you already have the carbocation intermediate where already carbon is attached to 3 groups. But now that is not the case. Now carbon is attached to 4 groups, right? So that is why here steric hindrance point you have to consider, and based on that 1 degree will give you better result, then 2 degree and 3 degree. And what type of condition will favor SN2? If you take, sorry, it is not non-polar, it is polar aprotic. So in both cases you have to take polar solvent, but now protic solvent we are not taking, we are taking aprotic. Now aprotic is obviously the opposite of protic. In protic, what we have said, that there must be some active hydrogen, that is hydrogen attached to some electronegative atom, oxygen or nitrogen. But in aprotic, that will not be the case. So if you take polar aprotic solvent, if you take strong nucleophile, remember in case of SN1 we have mentioned weak nucleophile, but now we are saying strong nucleophile, and the reason is now nucleophile concentration is mentioned in the rate determining step, and that is why we should take strong nucleophile and high concentration of nucleophile. So if concentration of nucleophile is very high, that means rate will also be very high. So all these conditions, it will favor SN2 mechanism. And one thing also I will like to mention, and that is the energy profile diagram. So if it is SN2, energy profile diagram means energy is in the y-axis and x-axis means reaction progress. That means as reaction is progressing. Now if this is the position of starting material, that is alkyl halide, and if this is the position of product, so see, starting material, suppose it is having energy at this position, product is having energy slightly lower than this, and the nature of the graph, it will be single humped graph. And the reason is, as it is single step reaction, so that is why the nature of the energy profile diagram, it will be like this. So this is the starting material, that is alkyl halide, this is the position of product, and this peak that you are seeing here, this is basically this transition state. So see, its energy is very high compared to starting material and product, so it is very unstable. And this energy, that is the difference between the energy of starting material and the transition state, this energy gap is basically activation energy. Okay, and if we see what is the energy profile diagram for SN1. Now SN1, it is involving two steps. So there will be two transition state. Okay. So this is the nature of the graph. Now let me write all these positions. This is starting material. This is TS1, that means transition state 1. This is transition state 2. This is product. And what is the position? This is actually the intermediate. So see, intermediate is having higher energy compared to starting material and product, but it is obviously lower in energy when you are comparing with TS1 or TS2. Now this is the activation energy for the first step. Energy difference between starting material and transition state 1. And this is the activation energy for the second step, which is the energy difference between intermediate and transition state 2. Now see, this energy gap is high and this energy gap is comparatively low. And why it is so? Because in SN1, remember what we have already mentioned, the first step is slow step and the second one is fast. And slow step means what? Here activation energy is high. So for the first one, this energy gap is high. Maybe my whatever I have drawn, it is not very clear, but activation energy for the first step is high. That is why it is slow, because to reach the transition state you have to provide high energy. And for the second one, the energy gap is low, so that is why it is fast step, FAST, not FIRST. Okay, so this is the difference between the energy profile diagram of these two types of reaction. And if you want to go into the details of transition state 1 and 2 in SN1, basically why I'm going into the details, because regarding energy profile diagram, there is question in the examination. So that is why you should have proper idea about it. So here I will, it is, if you consider this reaction for understanding the energy profile diagram, it will be better. So see, here we have total 2 steps. Now in the first step, this bond between carbon and X, this is just breaking. So this is intermediate I. This is starting material. So basically, if you want to know the transition state, which is actually not written here, it will be like this. That is, I'm writing in short, Me3C. There is a dotted line between carbon and halogen. Partial positive charge over carbon. Why partial positive charge? Because carbon X bond is not fully broken. It is just in the intermediate situation. That is by dotted line. And partial negative charge over leaving group. Double dagger sign, which means it is transition state. So this is the structure for the first transition state. And the second transition state, it will be like this. Now Me3C, the bond between carbon and nucleophile, it is just starting to form. So partial positive charge, partial negative charge, and double dagger sign. So this is transition state 2, which will be in between these two. Now if you write the transition state 1 and 2, then there will be 2 more arrows, but actually it is 2-step reaction. Fine. So energy profile diagram, is it clear? The difference between these two energy profile diagram? Next is stereochemical aspect. But before going into the details, you have to be familiar with some terms that are very common in stereochemistry. That is, in for organic molecules, when we consider stereochemistry, some terms are very important. And what is these terms? First, we'll see what is optically active compound. So compounds which can rotate the plane of polarized light, they are optically active. Okay, it's fine. But what is plane of polarized light? If you do not know that, then you will not be getting proper idea that why it is optically active. So you have to know first what is plane polarized light. Fine. Now when we take consider normal light, that is light waves, they are actually oscillating electric and magnetic field. So there is both oscillating electric field as well as magnetic field. Now when it is a normal ordinary white light, suppose, then the oscillation is randomly oriented in an infinite number of planes. So for simplicity, here we have taken only three colors: green, red and blue. So suppose you have three wavelengths, and when it is not plane polarized light, suppose it is unpolarized light, normal light, unpolarized light, because it is containing the infinite number of wavelengths, having infinite number of planes, but we cannot show you infinite, so that is why we have taken for simplicity only three. So when it is ordinary light, there is basically mixture of different wavelengths, but if there is a specific filter for this purpose, if this ordinary light is passed through a polarizer, which is basically acting as a filter, so what will happen now? All planes of the oscillation are filtered out except one. So as if this polarizer it is actually as if it is a filter. So now see, after this polarization filter with vertical passage, so here only this red wavelength is vertical, so that is why it can only come out after moving through this filter, but not the blue and green one. So now the light that you are getting, it is containing a single wavelength. So you can call it now linear polarized light with one plane of oscillation. So this is the plane in which it is oscillating. Okay. So right now we know what is the difference between plane polarized light and unpolarized light. Okay. So this is the difference. Now we will see what is optical, how we are getting optically active compound. So this is unpolarized light, because see, different directions wavelengths are there. Wavelengths are that is, waves are not drawn, but their direction is drawn, and several type directions are you can see here. Now this is a filter. After going through the filter, there is only one plane, that is only one wavelength will be there. And suppose in this part there is presence of a compound which is basically optically active. Now this direction is vertical, but after this wave is moving through this optically active solution, that is, the compound is basically in some solution and the wavelength is passing through this solution, and after that, if the molecule is optically active, it has the property to rotate this plane polarized light. So see, before going moving through this optically active compound solution, it is vertical, but now it is theta degree, it is, there is an angle by theta degree. Okay. So in this way, when it is optically active compound, it can rotate the plane of polarized light. But if it is not optically active compound, it will not have this type of property. Then even after moving through the solution, it will come out as it is. But if it is optically active, there will be some rotation. And this rotation here you can see it is rotating towards this direction, but it is not necessary. It can also move towards the other direction. Both are possible. Okay. There is some also other part in this picture, but you don't have to consider this part. Up to this is enough. Now depending on whether it is rotating the plane of polarized light to the right hand side or to the left hand side, in this case it is right hand side, it is rotating, but it may not be so. So when it is rotating the plane of polarized light to the right hand side, then it will be called dextro, which is denoted by small d, and if it is rotating left, it is called levo. Now it is easy to remember. Just remember left L and right R is D. Okay. Now sometimes you will see mention of some capital D or capital L, but don't be confused with these two. Capital D, capital L, completely different things. They are mostly used in carbohydrate chemistry, but here it has nothing to do. In this case, you have to use small d and small l. Don't use capital D or capital L for dextro LIVO. That will completely create some different meaning. Fine. So this is called dextro or LIVO, depending on in which direction it is rotating the plane polarized light. And there is another notation that also we can use, and that is R and S. Again, I am saying the small d and small l, it has nothing to do with R and S. And I am erasing these two, otherwise it will create confusion. Now R and S, if you want to know that any optically active compound, whether it is R configuration or S configuration, that you can do easily if you know proper structure of the molecule. But remember, this R configuration, S configuration, that is applicable only when it is optically active. If it is not optically active, no question of R and S, no question of D and L. If it is active, then only these questions arise. Now, chiral molecule you can also labeled as R and S designation. And how you can do so? So, if you want to know whether it is R or S, basically you don't have to go through all these procedure. This procedure is important. That is, you are using some polarizing filter, then you are getting plane polarized light, you are making some solution of the compound. All this you have to do if you want to know whether it is dextro or LIVO. But if you want to know whether it is R or S, you don't have to do all these things. So if you want to know R and S, what you have to do right now, we will see that. So this is the molecule we have taken here, which is glyceraldehyde. Now this glyceraldehyde, it has two OH group and one carbon aldehyde group. Now here this carbon is basically containing 4 different groups. What are these groups? One group is CHO aldehyde, another group is CH2H, third group is OH, and obviously there is H also. So when 4 different groups are attached to the carbon, that carbon you can call chiral carbon. Okay. Now once you know that it is chiral carbon, next step is to know whether it is R or S. So to understand R and S, you have to know the priority order of the groups. So here we have groups CHO, OH. Now OH is having more priority than CHO. CHO is having more priority than CH2OH. And CH2H is having more priority than H. Now if you are interested to know, that is how you will get the idea about the priority, that you can get from, there is a CIP rule for that, specific rule. From that you can easily understand the priority, but mostly it is dependent on the atomic mass. So here oxygen, which is directly attached to this chiral carbon, the first atom you have to consider, then you have carbon. So among these two, obviously OH will get priority. Then among CHO and CH2OH, here carbon is attached to one hydrogen and one OH, but here carbon is attached to two hydrogen, one OH. So obviously that is why CH is getting more priority. So we are not going into the details because that will be completely different topic. So this is the priority order. Now see here, all the groups are written in different color. Priority 1 in red color, priority 2 in blue color, priority 3 in it is gray, it is green, and H, which is least priority, that is in black color. Now for simplicity, you can also write the molecule in this way. Okay, so 4 groups in 4 different color, red, then blue, then green, and 4 least priority. Now when you already have reached this position, next what you will do, you have to keep the lowest priority group away from your site. So suppose when you are looking at this molecule, 4 is below the plane, dotted lines are there. So 4 is away from you, it is behind the screen. So under this condition, when the least priority group, in this case it is H, but not necessarily it will always be H. Okay, so in this case it is H, the lowest priority group, it is away from us. Under this condition, when you are moving from 1 to 2 to 3, if this is clockwise, it will be R, but if it is anti-clockwise, it will be S. So in this way, you can decide whether it is R or S. Now if you normally what happens if this particular molecule is R configuration, right? So if now you have taken it in this, you are making some solution of it, then some polar plane, it is plane polarized light is going through this, it will, suppose it is rotating, this theta angle is plus 30 degree. But if you have taken the same molecule but now it is S, it will rotate minus 30 degree. Okay, so this is the property for enantiomers, because here R and S isomer, these two are enantiomer. So if one enantiomer is rotating plus 30, another one will rotate minus 30. But here I am just writing it arbitrarily, that plus 30 for R. But don't assume that plus sign is always used for R. No, there is no such thing. I am just writing it arbitrarily. Okay, I am just trying to mention that if R is moving in one direction, then S will be moving the compound in another direction, and there will be just difference in sign but not the numerical. Fine. Now if you have equimolar mixture of these two isomers, suppose if you have equimolar mixture of R and S or D and L, then what will happen? It will make racemic mixture. That means in this sample, if you have both R and S 50%, 50%, now what will happen? One will rotate plus 30 degree, another will rotate minus 30 degree. So as a result, it will cancel each other. Ultimately, the neat result is 0. That means it is racemizing each other. But if it is not 50-50, suppose R is present 60%, S is present 40%. Now it will not balance each other completely. In that case, it is not racemization. But if it is 1:1 amount, it will be racemized mixture or racemic mixture. And the pair of two optically active isomers, they are basically having mirror image relationship with each other. They are also known as enantiomers. So R and S isomer, they will be enantiomer to each other. So in this slide, is there any doubt? Should I repeat any part? If all the substituent attached to that carbon, that is to any carbon actually, are different, the mirror image of the molecule is not superimposed or overlapped completely on the molecule. And in that case, you can call the carbon as asymmetric carbon or stereocenter. Now, the asymmetry of the molecule, along with the non-superimposability property of the mirror image, is responsible for the optical activity in such organic compounds. So when you have this type of asymmetry, and that is 4 different groups are attached to the carbon, that means all the substituents are different, because carbon can have maximum 4 substituents, right? And all the substituents are different. And the second thing is there will be non-superimposable relationship of the mirror image. So if this type of situation is there, then only you can say that the molecule is optically active. So here you will see 2 examples. One molecule is optically active, another one is not active. And we will try to see how they can be superimposed or cannot be superimposed. So the first molecule we have taken is carbon attached to hydrogen, fluorine, chlorine, bromine. That means all the 4 groups are different. So this carbon is chiral, star sign is given. Now if you have taken the mirror image, suppose this is 1, this is 1 prime. Mirror image. Now if you are doing 180-degree rotation, that means you are rotating like this. So now F is right hand side, Cl and Br towards left hand side, and also here Br is below the plane, but now it will be towards you. Previously Cl is towards you, now Cl is away from you. Now suppose it is I double prime. Okay, now I double prime and the original molecule, at a first glance it seems same, but actually it is not same. See, CH, CF, these 2 bonds are directly on the plane, that is fine. But in this case, Cl is away from you, Br is towards you, but here Br is away from you, Cl is towards you. So 1 and 1 double prime, they are not actually same, and they are also not cannot be superimposed on each other. If you are placing the molecule over this molecule, it will not be superimposed. Okay, so this is the property which is known as chirality or optical activity. But another molecule, now see, this molecule is carbon attached to H, fluorine, 2 chlorine. That means now 2 groups are same. So this is not chiral center. And now if you are taking the mirror image, and same thing if you are doing, suppose again you are doing 180-degree rotation. Now F will be this side, but these 2 groups are same. Now see, these 2 molecules you can easily superimpose. If you are placing the molecule over the other, it will be matching with all the substituents will be matching with each other. So chiral molecules are optically active, while the objects which are superimposable on their mirror images, they are not optically active. They are achiral, which is the opposite term of chiral. Just add a before C, and optically inactive. Okay, is this clear? Should I repeat? Now this stereochemical aspect, it is not complete yet. There will be further discussion. Some more discussion is left that we'll do in the next class. I'm just giving you some primary idea that 3 possibilities are there when you consider SN1 and SN2 mechanism. 3 possibilities are there, but you will see among these 3 possibilities, one is retention, then inversion, then racemization. For SN1, it is mainly racemization, that is 50-50 mixture of R and S. It will cancel out each other. Ultimately, it will be racemic. And for SN2, it is inversion. But there is another possibility which is retention, that also you have to know. Okay, so 3 different possibilities are there when a bond directly linked to an asymmetric carbon atom is broken. That is the carbon halogen bond that is present in alkyl halide. That carbon must be chiral. Otherwise, these questions are not arising. We are discussing stereochemical aspects. So the alkyl halide, that is Rx, that R part, the carbon with which halogen is attached, that carbon must be chiral center. Otherwise, stereochemical aspect, this question doesn't arise. Okay. So regarding all the slides, if there is any doubt, please mention. So as there is no doubt, we are ending the session here. Thank you for listening.